Hello, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of Mathematical Methods of Physics 2, with the course code PHY 222, we are at the lecture number 5, and the topic is complex form of Fourier series. In our previous lecture, we have seen that how we can expand a function, a periodic function, into Fourier series, and then how we can derive the formulas for the coefficients of each term. In today's lecture, we want to extend that procedure from normal cosine and sine form to the exponential complex form. So there are two methods to do that. The first method is to just put in the Euler's formula for sine and cosine into already derived formula for the coefficients and get the complex form. And the other method is to explicitly derive the complex form. So I will show you both. First, let's go towards the sines and cosines form, and then see that how we can implement the first method, where we put in the Euler formula for sine and cosine into the already derived formulas for the coefficients and get the required exponential form. So you know that the function sine and cos x can be represented as exponentials. For example, the sine x formula is like this. So you get 2 exponentials divided by 2 iota, and similarly for cos nx there is a plus sign in between. So these Euler formulas we can now substitute into the sine and cosine form of the coefficients and easily can get the exponential form. This is the simple method, and to illustrate it, let's recall the example from the previous lecture where we had a function and we expanded it into a Fourier series, and then we calculated all the coefficients, and the final form of that function was like this. If you remember, it was just a voltage function with the different frequencies, and this was the final form. And in this form, now what we can do is to plug in the values for sine x, sine 3x and sine 5x and get the exponential form. So I mean that over here, as you can see, that's sine nx. So for example, for n is equal to, let's say 1, what I will do that put in n is equal to 1 over here and get the sine 1x exponentials, and then plug in that one into here for sine nx, sine x. And similarly, then I can repeat the same procedure by for n is equal to 3 and get this sine 3x into the exponential form, and similarly for sine 5x and so on. So by this way we can transform this f of x from sine cosine form to the exponential form. So this is the first method, and relatively a simple method, where we've seen that just using Euler formula for sine and cos and already derived already expanded function, we can just replace the sine and cos terms and get the exponential form. But there is another explicit method where we can derive the formula without using this f of x already expanded function. We can also directly derive it. For this, we first of all need to expand a given function f of x into exponentials. So rather than expanding the function into the sines and cosines form, we can expand this function. We have to expand this function in terms of exponentials like this. You can see over here that this f of x is then c naught is the first coefficient, and then e raised to power 0x, because this term is for n is equal to 1, n is equal to 0, and then we have the second term where we have n is equal to 1, and so on. You can see that these other coefficients will come with a negative sign, because there we can have also c n is equal to -1, this is minus c minus 1, and e raised to power minus I or iota x, and c2 then positive and then negative, and so on. So if we expand the function like this into exponentials and also with minus n's, then the formula for our this can be written as a sum from minus infinity to plus infinity, and Cn is equal to e raised to power minus nx. And the next thing is to calculate all these coefficients. So remember that in sine cosine form, what we have done is to expand the function into sines and cosine form, and then calculate the coefficients of cosine series, that is a0, a1, a2 up to an, and then the coefficients of the sine series, that is b1, b2 and up to bn. But now since we have exponential expansion, where we have now coefficients c, c1, c2, c3 and c minus 1, c minus 2 up to c minus n, and now we have to calculate all these coefficients. So let's start with the first coefficient, that is c naught. For this coefficient, first of all, what we have to do, again the procedure is same, where we have to find out the average values. So this in the expansion we have to take average term by term, and we will see that most of them will turn out equal to 0, or all of them will turn out equal to 0 in fact, except the term which contains that particular coefficient, that specific coefficient we want to calculate. So for example, over here you can see that if we have this function and we want to calculate c naught, so the thing is that we have to calculate the average values of this function term by term. So if you calculate the average value of the first term, this will be like this, and the average values of the rest of the terms, that is containing e raised to power iota kx with k as an integer and not equal to 0, but we get that all of them are equal to 0. So only first term survives, and that is c naught, and all other terms which contains exponentials e raised to power kx, their average values are equal to 0. And this we have already shown, if you remember. In the previous lecture I have shown you that the exponentials go away, these vanishes, all these values, their average values actually vanish. So we got the first coefficient c naught in exponential form by this procedure, which is equal to this one, and you can see that this matches actually with the a naught, because actually c naught is in fact real, it's not really having a imaginary part. And now we proceed and go towards the second coefficient, that is equal to c1, and see how we can calculate its value. By now you have got the method, and the method is that to multiply each term with that value, that putting n is equal to that value, and calculate the average values of each term, and what you will see that all the terms vanish except that term which contains that particular coefficient. So saying it again, multiplying each term with e raised to power minus I n x, so it depends what is the value of n. So if you are doing it for e raised to power I 1x, then you will put n is equal to 1 and multiply each term with e raised to power iota minus iota x. Particularly note this minus sign over here, we have included minus sign over here, and what will happen that particular term will not vanish and the other will be equal to 0, and then we find the average values then of the each term, then all terms go to 0 except that particular term, and we will get that particular coefficient. So for example, over here you can see that we have multiplied this function with e raised to power minus iota nx, and then what happens that we get this e raised to power minus iota nx on the right side into each term multiplied with each term. You can see into the first term and the second term with the c1, and with the third term c minus 1 coefficient, and so on. And what we get is that all terms are 0 except cn. That is because we have multiplied with the cn. Remember, if you multiply with this e raised to power iota 1x, then this first term, this will 1x will not be 0, and all other will be 0. And if you multiply with the e raised to power iota 2x, then the 2x will not be 0, and so on. So since I am showing you it for the general coefficient, so all terms are 0 except cn. And you can then find out the coefficient cn if you calculate this integral, which you can see is rather very simple because of this minus and plus sign, and they just go away, and we get this integral over here equal to 2 pi, and then cn value is this one. So you have seen now that the coefficient general formula, we have formulas we have already derived, and that simple and standard procedure that multiplying each term with some exponential and then taking the average values, all terms goes to 0 except that particular term. So I have shown you this for the general term where you have seen, and the first term where you have seen that we get the we got the formulas for the coefficients in complex form. Okay, so once we have now done this, now it's interesting to check that example which we have done directly in the beginning of this lecture, where we taken the function which we have already expanded an exponential form, and just using the Euler formulas we have transformed that into the exponential form. But now since we have got the coefficients, Fourier coefficients into exponential form directly, so we see that if we take the same function, expand it, and use these Fourier coefficients, can we get the reverse? That does this equal to is it equal to the form sine cosine form? So let's check, and what you will see that this function, this is the function we are using. This is an example. This is the interval, and the expansion was in the sine cosine form, but now since we got the coefficients in the exponential form, so we need to calculate the coefficients. So for example, cn, if we calculate its integral, we have to split it as we have done in the sine cosine form, and after the splitting and calculate, this first term goes away, and the second integral is very simple. And if you calculate it, you get the when n is odd, this value, and when n is even, this value. And if you so you got the c naught value is equal to 1 over 2, and if you put it into the expansion, what you get into this expansion what you get is this series, and this series, this is with the positive and with the negative, and if you substitute the Euler formulas for each sine and cosine term, and put it into this expanded exponential form, then these terms survive, are just equal to the sine cosine form. So we have seen that in exponential form the coefficients match exactly with the coefficients in the sine cosine form. So by this we now know that there are two methods. Sometimes it's convenient to use one of them. For example, sine cosine form could be a better choice, but in some cases it is good to expand that into exponential form and then use it. But in any case, both of them gave the same results. Okay, so far so good. So now we have seen the exponential form of the Fourier coefficients, and there is another interesting point which we have made in the last lecture, that so far we have used the functions which were 2 pi periodic, but I told you that other intervals are also possible, usually the shorter intervals for the sine and cosine. So now I want to show you that how other intervals are possible and what are the modifications we have to make in order to incorporate these other intervals. So we can change period to other intervals very easily. So for example, in this sine function you can see that we have n pi x by L. So here our interval is basically 2L, and now it's not 2 pi and it's general interval 2L. And let's see that how the whole procedure of finding Fourier coefficients will change for having this different interval. It's very easy, it's not a big change, but let's check it. So our sine can be written into this form as well. You can because this is the period 2L, and if you take this you can simply write this equal to pi form, multiplying pi inside, and then it's just equal to psi n pi x by L, because it's repeat itself after this interval. And then what we want to do is to expand our function, and this expanded function in this new interval is equal to this series. This is the first term, second term, and now you see this L coming downstairs everywhere. So this is because we have a different interval than 2 pi, and now you understand the reason that in the beginning I just used the 2 pi, because to make the things look easier. And this expanded function into this different interval is now of this form. So just you see that in the argument of sine and cosine we got this L downstairs every term. So the function can be written this in the sum form, series form, and now the point is to find out the average values. And to find out average value, we replace this 1 over 2 pi minus pi to plus pi by 1 over 2L minus L to plus L, because now this is the new interval, we are using a different interval. And so we have to take the average of all of the terms, each and every term, in order to calculate these in different interval. But since we know that the average of the square of the sine and cosine is equal to 1 by 2, so from here you can see that these two terms just cancel out, equal and is equal to 1, and the coefficients then become the an, bn and cn of you can see that 1 over L coming in front of an and bn, and then cos and sine just their arguments divided by L, and this Cn, this is the complex form. So I have shown you all the three formulas for the An, Bn in sine cosine form, and Cn into the complex form. So it's not a big difference, but just a number L coming here in all formulas. So now it is important to also do a simple example with this different interval. So let's go back to our function which we as example which we are using, but now in a different period, that is 2L, different interval. This one you can see just now we are using a different interval, and we can sketch this function. You can see this is the sketch and showing you the interval when it is 0 and when it is 1. And after the sketch we can calculate now the coefficients, all these coefficients Cn into the exponential form, and again you are seeing that splitting it and then calculating this integral, and it's very simple. And two cases, when n is even and when n is odd, you get the values of these coefficients Cn, and C naught especially is equal to 1 over 2. It's very simple again to calculate this integral. And if you put back this into the expansion, you see that this is how this expansion looks like, and now it's a different interval. but procedure, all the procedure is the same. Just multiply the terms with a particular exponential and take the average values, and you will get the required coefficients. And these are the references. So to recall what we have learned today was that first of all, I shown you that the exponential form of the Fourier coefficients is possible, and we can calculate it by the two methods. One is a simple method where we just use the Euler formula and already expanded sine and cosine form. We put it in there and we get the exponential form. And the second was to do it from the very beginning, expand the function into the exponentials, and then these calculate the each term, all the coefficients in each term, and but the procedure was the same, that multiply with a particular exponential and calculate the average values. All of them will go to 0 except that particular term, and by that way we were able to calculate the Fourier coefficients in exponential form. And in the second part of the lecture, I have also shown you that how we can modify the whole procedure for other intervals, and you have seen that it was very simple. Just we have defined the other interval, and the procedure was same for calculating the coefficients. At the end, we got the expanded function, another interval, into Fourier series and all the coefficients. With this, I thank you all.